Introduction to Data Structures and Algorithms. Welcome to the world of data structures and algorithms, a foundational subject in computer science that forms the backbone of efficient software development. In this audiobook, we will embark on a journey that will take us through a wide range of concepts, from basic data structures like arrays and linked lists, to more complex topics like trees, graphs, and sorting algorithms. Let's start by understanding what data structures and algorithms are, and why they matter. What is a data structure? A data structure is a particular way of organizing and storing data in a computer so that it can be used efficiently. Think of it like a container for your data. Depending on the problem you're trying to solve, you may choose a different type of container. Imagine you're managing a library. You could organize the books by title, author, genre, or the year they were published. The way you organize the books represents your data structure. Now, the choice of data structure determines how efficiently you can retrieve or update information. For example, if the books are stored randomly, finding a particular one will take time. However, if the books are organized alphabetically, the process becomes much faster. Similarly, in computer science, the right data structure allows you to access and modify data in the most optimal way. The key types of data structures include 1. Arrays. 2. Linked lists. 3. Stacks and queues. 4. Hash tables. 5. Trees. 6. Graphs. Each of these structures has its own advantages and trade-offs. Throughout this audiobook, we will explore them in detail, focusing on how and when to use each one. What is an algorithm? An algorithm is a step-by-step procedure or formula for solving a particular problem. It is essentially a well-defined set of rules or instructions that we follow to achieve a goal, similar to a recipe in cooking or an instruction manual. In the context of computer science, algorithms work on data structures. They are designed to perform operations like searching, sorting, or modifying data. For instance, searching for a book in our library example could be thought of as an algorithm, and depending on the data structure you've chosen, this algorithm may be more or less efficient. Some of the common categories of algorithms are 1. Sorting algorithms. For example, quicksort, merge sort, bubble sort. 2. Searching algorithms. For example, binary search, linear search. Graph algorithms. For example, Dijkstra's algorithm, depth first search. 4. Dynamic programming algorithms. For example, Fibonacci sequence, knapsack problem. By combining data structures with algorithms, we create systems that can perform tasks efficiently, even when faced with massive amounts of data. Why efficiency matters? As software engineers, our goal is not just to solve a problem, but to solve it efficiently. A solution that works on small amounts of data but fails or becomes too slow as the input size grows is often unusable in real-world applications. Imagine a company like Google processing millions of search queries per second. The algorithms and data structures behind Google Search must be extremely efficient to handle this scale. This is why we care about performance, and why we focus on selecting the right algorithms and data structures for the job. Efficiency is often measured using Big O notation, which describes how the performance of an algorithm scales with the size of the input. We will cover Big O in detail in a later chapter. Arrays and linked lists. In this chapter, we will begin our exploration of data structures with two of the most fundamental types, arrays and linked lists. Arrays. An array is a collection of elements, each identified by an index. It is one of the simplest and most widely used data structures in programming. Arrays are excellent when you need to store a fixed-size collection of elements that you can access by index. In an array, accessing an element by its index takes constant time, denoted as O1, which makes arrays very fast for retrieving elements. Let's look at an example. Imagine an array of integers 5, 12, 3, 8, 7. Here, the index starts at 0, so the element at index 0 is 5, the element at index 1 is 12, and so on. If you want to retrieve the third element, you simply access it by its index, which takes constant time. Advantages of arrays. A. Fast access. You can access any element in constant time, as long as you know the index. B. Simple structure. Arrays are easy to understand and use. Disadvantages of arrays. A. Fixed size. Once you create an array, its size cannot be changed. If you need to add more elements, you'll have to create a new, larger array and copy over the elements. B. Costly insertions and deletions. Inserting or deleting an element in the middle of an array is inefficient because all the subsequent elements need to be shifted. Linked lists. A linked list is a data structure in which each element, called a node, contains a data value and a reference, or pointer, to the next node in the sequence. Unlike arrays, linked lists do not store elements in contiguous memory locations. This allows them to be more flexible with memory, but accessing elements by index is slower because you need to traverse the list to reach the desired node. Example of a singly linked list. Let's create a simple linked list. 5, greater than 12, greater than 3, greater than 8, greater than 7, greater than null. Each node contains a value, for example, 5, 12, and a pointer to the next node. The last node points to null, which signifies the end of the list. Advantages of linked lists. A. Dynamic size. Linked lists can grow or shrink as needed, without needing to allocate a fixed amount of memory ahead of time. B. Efficient insertions/deletions. Inserting or deleting elements, especially at the beginning of the list, is very efficient and takes constant time. 1. Disadvantages of linked lists. A. Slow access. To access an element in a linked list, you must traverse the list starting from the head. This results in linear time complexity, (ON), for access by index. B. Extra memory. Each node in a linked list requires extra memory for storing the pointer to the next node. Arrays versus linked lists. Let's briefly compare arrays and linked lists. Arrays are great when you need quick access to elements by index and know the size of your data ahead of time. Linked lists, on the other hand, are more flexible when it comes to size, but accessing elements is slower. Both arrays and linked lists are fundamental building blocks for more complex data structures, so understanding their strengths and weaknesses will help you make informed choices when designing algorithms. Stacks and queues. In this chapter, we will discuss two essential data structures, stacks and queues. These structures are commonly used in algorithm design and are based on simple but powerful principles. Stacks. A stack is a linear data structure that follows the last in, first out, LIFO, principle. The last element added to the stack is the first one to be removed. A stack operates much like a stack of plates. The last plate placed on the top of the stack is the first one you take off. In a stack, elements are added, or pushed, to the top, and removed, or popped, from the top as well. Let's look at the primary operations that can be performed on a stack. A. Push. Add an element to the top of the stack. B. Pop. Remove the top element from the stack. C. Peek. Look at the top element without removing it. D. Is empty. Check if the stack is empty. Example use cases of stacks. 1. Function call stack. In programming, when a function is called, its details are pushed onto the call stack. When the function completes, its details are popped off. This allows programs to handle recursive function calls efficiently. 2. Undo/redo functionality. Many applications, such as text editors, use stacks to implement undo and redo features. Each action is pushed onto a stack, and when you hit undo, the most recent action is popped off the stack. Time complexity of stack operations. 1. Push, 1. 2. Pop, 1. 3. Peek, 1. 4. Is empty, 1. Stacks are ideal when you need to manage data in a LIFO manner, where the last piece of data you work with is the first to be removed. 3.2 Queues. A queue is another fundamental data structure that follows the first in, first out, FIFO, principle. In a queue, elements are added at the rear, or back, and removed from the front. Imagine a queue in real life, like waiting in line at a grocery store. The first person in line is the first one to be served. Here are the primary operations of a queue. 1. Enqueue. Add an element to the back of the queue. 2. Dequeue. Remove the front element from the queue. 3. Peek. View the front element without removing it. 4. Is empty. Check if the queue is empty. Example use cases of queues. 1. Task scheduling. In operating systems, processes are often managed using queues. The first task to be added to the queue will be the first one process. 2. Breadth first search, BFS. A queue is often used in algorithms like breadth first search for traversing graphs or trees level by level. 3. Print queues. Printers often use a queue to manage print jobs. The first job sent to the printer is the first one to be printed. Time complexity of queue operations. 1. Enqueue, 1. 2. Dequeue, 1. 3. Peek, 1. 4. Is empty, 1. Queues are incredibly useful when you need to maintain an order where the first item in is the first item out, such as in scheduling systems or breadth-first traversal algorithms. Trees and binary search trees. In this chapter, we will dive into more complex data structures, trees and binary search trees, BSTs. Trees are hierarchical structures that are essential in solving a wide range of problems in computer science. Introduction to trees. A tree is a nonlinear data structure that consists of nodes connected by edges. Each tree has a root node, which is the topmost node in the hierarchy, and each node can have child nodes. A node without children is called a leaf node. The key characteristics of a tree are: 1. Root. the topmost node of the tree. 2. Parent, a node that has children. 3. Child, a node that is a descendant of another node. 4. Leaf, a node with no children. 5. Subtree, a portion of the tree that consists of a node and all its descendants. Trees are used in a variety of applications, including hierarchical data representation, parsing expressions, and managing relationships between entities. Binary trees. A binary tree is a special type of tree in which each node has at most 2 children, referred to as the left child and the right child. Binary trees are widely used in algorithms because of their simplicity and efficiency in structuring data. Each node in this binary tree has at most 2 children. This type of structure is the foundation for more advanced trees, like the binary search tree. Binary search trees, BSTs. A binary search tree, BST, is a type of binary tree where each node satisfies the following property. For any node with value x, the left subtree contains nodes with values less than x, the right subtree contains nodes with values greater than x. This property makes searching in a binary search tree very efficient, as you can have the search space with each comparison, similar to a binary search on a sorted array. Operations in a binary search tree. 1. Search. To find a value in the BST, you compare the value with the root. If it's smaller, you go to the left subtree. If it's larger, you go to the right subtree. This makes the search operation efficient, with a time complexity of O log n, for a balanced tree. 2. Insertion. Inserting a new value involves traversing the tree to find the correct position while maintaining the BST property. 3. Deletion. Deleting a node requires handling special cases, such as deleting leaf nodes or nodes with 1 or 2 children, while keeping the tree structured properly. Advantages of BSTs. 1. Efficient searching, insertion, and deletion operations, all in O log n, time for balanced trees. 2. Ordered structure makes an ordered traversal, left, root, right, easy, which results in sorted order output of elements. Graphs. In this chapter, we'll explore graphs, one of the most versatile and widely used data structures. A graph consists of vertices, nodes, and edges, connections, between them. Graphs are used to model networks, such as social networks, communication networks, transportation systems, and even web page links. What is a graph? A graph is a collection of vertices, also called nodes, connected by edges. Graphs can be classified into 2 types. 1. Directed graph, digraph. In a directed graph, each edge has a direction, meaning that if there is an edge from vertex A to vertex B, you can travel from A to B but not necessarily from B to A. 2. Undirected graph. In an undirected graph, edges have no direction, meaning you can traverse between vertices in both directions. Key concepts in graphs. 1. Vertex, node, a point in the graph. 2. Edge, a connection between 2 vertices. 3. Path, a sequence of vertices connected by edges. 4. Cycle, a path that starts and ends at the same vertex. Applications of graphs. 1. Social networks. Graphs are used to represent relationships between people. 2. Navigation systems. Road networks can be modeled using graphs, where intersections are vertices, and roads are edges. Web crawling. The web can be represented as a graph, where web pages are vertices, and hyperlinks are edges connecting them. Strings, the foundation of text. Think of a string as a simple chain of characters. You can picture it like a necklace, where each bead is a character, letters, numbers, or even symbols. Strings are one of the most basic data structures used to store and manipulate text. They're essential in programming, because they're the foundation of text processing. Whether you're working with a person's name, a sentence, or a paragraph, you're dealing with strings. Strings also support a variety of operations, like concatenation, linking 2 strings together, searching, finding a character or substring, and slicing, extracting parts of the string. But while strings seem simple, they're the building blocks of more complex structures we'll dive into later. Heaps, the priority queue. A heap is a specialized tree-based data structure that is particularly useful when you need to quickly access the largest or smallest element in a collection. There are 2 types of heaps: max heaps, where the largest element is always at the root, and min heaps, where the smallest is at the root. Picture a heap like a mountain. At the very top of the max heap mountain is the largest boulder. If you need the next largest boulder, you can efficiently slide down and retrieve it. Heaps are commonly used in algorithms like Dijkstra's shortest path or for implementing priority queues. Inserting and removing elements from a heap is efficient, with a time complexity of O log n. Segment tree. Range query expert. A segment tree is a powerful data structure used for answering range queries efficiently. Imagine you have a list of numbers, and you want to be able to quickly find the sum, minimum, or maximum of any range within that list. Instead of recalculating these values from scratch every time, a segment tree allows you to store pre-computed information in a hierarchical structure. Think of a segment tree like an organizational chart for a company. At the top, you have the CEO, representing the entire list, and as you move down, each node represents progressively smaller ranges, until the leaves of the tree represent individual elements. This allows you to quickly update and query data ranges in logarithmic time. Trie, the dictionary of prefixes. A trie, pronounced trie, is a tree-like data structure used to store dynamic sets of strings, often for fast retrieval of words based on prefixes. It's particularly useful in applications like autocomplete, where you want to find all words that start with a given prefix. Picture a trie as a family tree, but instead of representing people, it represents letters of words. Each node in the trie represents a single character, and paths down the tree form entire words. The beauty of a trie is that it can efficiently store common prefixes only once, saving memory and speeding up search operations. Suffix array, a compact index for string search. A suffix array is an array of all the suffixes of a string, sorted in lexicographical order. Imagine taking a word like banana and writing down all its suffixes, like banana, anana, nana, and so on. Then, you sort these suffixes alphabetically. The result is a suffix array, which provides a way to efficiently search for substrings. Suffix arrays are particularly useful in full-text searching, pattern matching, and bioinformatics, like searching for DNA sequences. While constructing a suffix array takes some time, once it's built, searching for any substring becomes very fast. Suffix tree, a tree for all suffixes. A suffix tree is closely related to the suffix array, but it's structured as a tree rather than an array. Every suffix of a string is represented by a path from the root of the tree to a leaf node. This data structure allows for fast searching of substrings, as well as other operations like finding the longest repeated substring. AVL tree, the balanced warrior. An AVL tree is a self-balancing binary search tree, named after its inventors, Adelson Velsky and Landis. Imagine a standard binary search tree, BST, where the left child is smaller, and the right child is larger. However, unlike a regular BST, an AVL tree ensures that the height difference, or balance factor, between the left and right subtrees of any node is no more than 1. This balance is crucial because it guarantees that the operations like insertion, deletion, and lookup can always be performed in logarithmic time. If the tree becomes unbalanced after an insertion or deletion, AVL trees perform rotations to restore balance. This makes them a great choice when you need a balanced tree and can't afford performance degradation due to skewed trees. Splay tree, the adaptive tree. A splay tree is another type of binary search tree, but with a twist. It self-adjusts based on usage patterns. Every time you access a node, the tree rearranges itself, pulling the accessed node up to the root using a series of rotations. This is known as splaying. The beauty of splay trees is that frequently accessed elements move closer to the root, making future accesses faster. This property makes splay trees efficient in scenarios where certain elements are accessed repeatedly, such as in caches, where recently used elements are likely to be reused. While individual operations may not always be optimal, the amortized time complexity for access, insertion, and deletion is logarithmic over a series of operations. B-tree, the giant of disk storage. A B-tree is a self-balancing tree data structure, optimized for systems that read and write large blocks of data, like databases and file systems. Unlike binary search trees, where each node has 2 children, B-trees allow each node to have multiple children, making them broader and shallower. This means fewer accesses are needed to reach any given data point. B-trees are structured to minimize disk reads, which is why they are widely used in databases and file systems that deal with large volumes of data. They allow searches, insertions, deletions, and sequential access in logarithmic time. A key feature of B-trees is that they keep data sorted and allow searches, sequential access, insertions, and deletions in optimal time even for massive datasets. Red-black tree, the colorful balancer. A red-black tree is another type of self-balancing binary search tree. In this tree, every node is colored either red or black, and the tree follows certain rules to ensure balance. For example, no 2 consecutive red nodes can appear on the same path, and every path from the root to a leaf must have the same number of black nodes. These color-based rules ensure that the tree remains balanced, with the height of the tree being logarithmic in the number of nodes. This guarantees efficient operations like searching, insertion, and deletion. Red-black trees are commonly used in memory management systems, as they provide reliable performance even under heavy workloads. One advantage over AVL trees is that red-black trees allow for faster insertions and deletions due to their less strict balancing rules. K-dimensional tree, KD tree, Navigating multidimensional spaces. A KD tree is a space partitioning data structure used to organize points in a k-dimensional space. Imagine you're working with data points that have more than 2 dimensions, such as in 3D graphics or machine learning, where each point could have coordinates like x, y, z. A KD tree helps you store and search through these points efficiently. The tree is built by recursively splitting the data points along different dimensions. For instance, in a 2D KD tree, you might first split the points along the x-axis, then along the y-axis, and continue alternating. This makes it easy to perform range searches, nearest neighbor searches, and other operations in multidimensional space. KD trees are widely used in applications like computer graphics, geographic information systems, and machine learning algorithms.